Pronto, pronto?
Esatto.
Ciao,
E così
mi
loro si
sentite?
sentono quelli che sono...
Ah, ok.
Mm. E quando fanno le domande, in modo che si sentano anche le domande su, appunto in streaming, bisogna
Passiamo in giro un altro.
passare esatto.
Ha abbastanza batteria per rimanere sempre
Secondo
acceso?
me, ah no, no, è meglio
Ok.
tenerlo spento poi accenderlo. Ma dovrebbe essere passato Marco stamattina anche con noi, a controllare tutto perché avevo organizzato. Esatto, sì, lui fa una sorta di regia da Zoom del suo studio, quindi perché c'è anche quello, se stai alla lavagna
direi che funziona. Mi sentite? Sì. Allora, grazie di essere qui. Oggi abbiamo il piacere di avere un seminario da parte del professor Marco Raveri, che ha preso servizio di recente qui al Dipartimento di Fisica e, come sapete, è una delle persone reclutate nell'ambito del progetto di eccellenza 2018-22 e ci racconterà un pochino le sue attività di ricerca. E niente, ti lascio subito la parola. Credo che ci sia anche la streaming YouTube e il seminario sarà anche registrato, così in futuro, se qualcuno lo vuol vedere, sarà disponibile. Prego.
Okay, grazie mille Silvano. Good afternoon everybody. I am really happy about giving this talk and I want to start by thanking you all for the warm welcome that I got in Genova as I moved to Genova. And you know, after settling life throughout the last month, I'm really happy that today I get to tell you basically what I do for a living. And this talk will cover about half of it. The half that's concerned with trying to learn something about fundamental physics from cosmological experiments. And in particular, what's concerned with gravity at larger scales in our universe. And if we are interested in fundamental physics, our universe is the perfect physical laboratory to study that and to get something out of it. Because according to the standard cosmological model that we have nowadays, our universe goes through a phase of inflation, of accelerated expansion that exposes energy scales that are beyond the reach of any Earth-sized experiments. And then after this period of inflation where quantum fluctuations are amplified to cosmological scales, our universe goes through a phase of nucleosynthesis of atoms, recombination of hydrogen, and then it enters a dark age where the dynamics of our universe is dominated by dark components, dark matter and dark energy. Dark matter giving the gravitational infrastructure for structures to form and galaxies to form, and dark energy to fuel the accelerated expansion of the universe. And as we see here, the universe goes through an incredible range of scales, allowing us to probe many different scales and you know, physical phenomena at many different scales. And the picture behind this picture of the universe that we have is called the standard lambda CDM cosmological model, because of the two dark components that I've told you in the previous slide: dark energy that makes up today most of the energy budget of the universe, and dark matter that makes about 25% of the energy budget of the universe. And the nature of these two components is so far unknown. We only have vague information on how these behave at cosmological scales, but we haven't detected these directly on the Earth, and we basically just know some of the properties of these elements. But fortunately enough, there's a gigantic experimental effort that was started by the cosmology community to try to understand what happens with these dark components of the universe. And the idea of this gigantic experimental effort is to map the universe to ultimate precision in the next basically 40 years, starting from the cosmic microwave background with many different experiments throughout the line to the clustering of cosmological structures. And the cosmic microwave background, as you might know, gives us a snapshot of when the universe was burning. And it's released from matter after light last scatters of hydrogen atoms, and it's free to free stream us to us, giving us a clean picture of what the universe was like about 300,000 years after the Big Bang. And this microwave background has been mapped by the Planck experiment to very high precision, and I've been involved into the next stage of these type of experiments that go under the umbrella of CMB-S4, whose aim is to map not only light but also polarization of light to basically ultimate precision. And for these experiments, which is an array of telescopes, I led in the past the working group that was tasked with understanding the performances of these experiments when it comes to testing dark energy and gravity models. And today I am a member of the Diversity, Equity, and Inclusion Committee of the CMB collaboration. Oops. On the other side, the way in which we probe the large-scale structures in our universe today mostly comes from gravitational lensing. As light travels through from either the CMB or from other galaxies, as light travels through the universe, it encounters massive structures that deflect that light. And what we see when we receive that light is a slightly distorted picture of the background galaxies, and that allows us to map the density content of our universe, and mostly the dark matter over densities along our line of sight. And in this respect, I've been working a lot with the Dark Energy Survey, which is today the state of the art of this type of weak lensing surveys. And it's a large digital camera on a telescope, and it just finished mapping the position of about 300 million galaxies. And here you see the whole sky, our galaxy, and this is the DES footprint to give you a scale of this endeavor. And here you see the distribution of dark matter as it's imaged through this effect of gravitational lensing. And inside the Dark Energy Survey, I have led the tensions working group, and what this tension means, it's going to be clear in a second. And it's a news of about a couple of days that I got nominated to lead the extension team, which is in charge of doing dark energy searches, which I think it's a very big deal. It's the dark energy searches for the Dark Energy Survey. It's like what it's built for. So I'm really happy to share this with you. And with this in mind, most of my work in the past years has been concerned in how do we extract fundamental physics information from these type of measurements. And throughout my searches, I've basically stumbled upon 3 strategies that I want to discuss with you today. And the first strategy is basically to grow tensions. And this is very familiar to the cosmology community, because we find from time to time slight discrepancies between different experiments measuring supposedly the same thing. And one way of looking beyond our standard cosmological model basically consists in just waiting for these tensions to grow, and grow in statistical significance until we can make a discovery. The second way in which we've been testing models of dark energy and gravity is basically model-based testing. So we take a model and we test the model against the observations we have, and then what I want to really tell you about today, which is model learning, which we'll come back in a second. So I want to give you some more details about these different strategies. Okay, so the first strategy is to just grow tensions, and in this respect I have to mention that in cosmology we have nowadays plenty of tensions, and which are basically summarized in this picture here. Here you see the expansion rate of the universe, the Hubble constant, as it's measured in blue from the Planck satellite, from CMB observations, and how it's measured through local distance ladder measurements, right, in this corner here. On the other hand, we can measure the amplitude of the clustering of structure, the amplitude of the density contrast of galaxies in our universe. And then we can measure that through CMB observations. We can measure it directly, for example, from the Dark Energy Survey. And these 2 measurements are simply different from this one. And statistical significance starts being fairly high, while the tension over the amplitude of the growth of structures is basically at the 2 to 3 sigma level. The tension over the determination of the Hubble constant is at, ranges today from 4 to 5 sigma, which is basically at the discovery threshold. And oops, why? Okay, I have to be very careful with this guy. And so I'll tell you briefly about these two tensions, because these will orient our discussion of the phenomenology you'll see later. The Hubble constant tension is the only parameter in our standard cosmological model which has physical dimensions. It has physical dimensions of time to the -1, right? So it's really a matter, measuring the Hubble constant is really a matter of providing an absolute calibration of our observations. And the CMB, and the CMB measures the Hubble constant because we measure temperature fluctuations, which is an absolute number, right? It has physical dimensions. And the scale of the acoustic peaks of the CMB and the spacing and the heights of these different peaks are sensitive to physics pre-recombination and basically the distance to recombination. And we can join them together, and we can join these two informations together to get a determination of the Hubble constant. And it basically goes this way, right? We have physical densities which are parameterized in terms of relative densities times the Hubble constant. The CMB is sensitive through, by assuming pre-recombination physics, it's sensitive to these physical densities and measures them, while the distance to the last scattering surface, so the distance to where the CMB was emitted, would depend on relative densities. So you can basically, it's a simple exercise to join these two numbers and get the value of the Hubble constant. And if you go through this exercise, with the CMB and through local measurements, what we find is basically an 8% discrepancy detected at 5 sigma. While on the other hand, I want to give you a flavor of what's the tension over the growth of structures, and with this very precise proxy, I want to convince you that we are measuring the amplitude of fluctuations in the CMB, right? These all band powers, this is a power spectrum, this tells us the amplitude of fluctuations, these data points are different from 0. And then we can also measure the amplitude of fluctuations in the late universe through large-scale structure surveys. And again, with this simple proxy, I want to convince you that yes, we are measuring the amplitude of fluctuations in the late universe. And when you combine these two, you get these two different determinations of the parameters relevant to these tensions, and they are somewhat different. In this case, the exercise of understanding whether these two experiments are in tension or not is not as easy as before, because we don't really have just one parameter that enters the game, but it's a slightly more complicated statistical exercise. But once you go through that, then the result is that there's again a 5 to 10% discrepancy over the growth of structures, which is detected at about 3 sigma. Along the way, I've become sort of an expert. An expert on, how you determine these types of tensions, because in case where we have, many parameters and many different degeneracies, but that's unfortunate, and that's, a story that got me through topics in statistics and machine learning, but it's unfortunately a story for another time. But I'll be happy to talk about these things with you guys if you're interested. Okay, so the pros of just sitting down and waiting for these tensions to grow until we sort of understand them. These strategies has some pros and cons. And one of the pros is that it's truly model independent. We don't really need to assume any physics beyond the standard model. We just use our standard model and we wait for tensions to grow. And it's sufficient in the sense that it forces us to look beyond the standard model if these tensions become very significant. On the other side, it's really degenerate with systematics. There's no benchmark to tell whether what we see is a discrepancy that's due to unresolved systematic effects or new physics, right? So we have no way of distinguishing these two cases. And on the other hand, it's inefficient, right? There's no first principle for which old physics should look like new physics. So if these two don't really look like each other, we might be missing features. And then it would just take longer for us to discover new things. On the other hand, model testing at least solves one of these problems, which is if we take a model, we test the model against cosmological observations, and we see if that works or not, that has a very clear cut with systematics. We can have model for systematics, we have a model for physics, and we see who works best, right? But on the other hand, you know, if we pursue this strategy, there's no really guarantee. The success of model testing relies on picking the right model. And this means that you're either right or lucky. And I've done this exercise many, many times for many, many different models. I have ruled out about one model every 2 years. And I can tell you I was nor right nor lucky. So I had to come up with some better strategy, which is model learning that I want to tell you about today. And this consists in taking, instead of taking a model, taking a whole family of models and trying to learn the properties of this family of models from the data. And you know, there's on the pro side of these type of things, there's guarantees. If a data feature can be explained by a whole class of models, then that feature will be picked up, right? And you know, this includes also the two previous approaches, because basically it will, you know, these type of model learning techniques will try to fit features, will try to fit tensions that appear. And of course, you know, as cons, we'll end up with larger error bars because the freedom we have in specifying a family of models is much larger than the freedom we have in specifying a single model, of course, which means our error bars will generally blow up. And obviously, it's significantly much more complicated, as I will try to convince you in 5 minutes. So I want to show you two worked examples of this process of model learning from cosmological observations. And I'll show you one that's purely phenomenological and one that's more connected to the physics, to gravitational physics and to dark energy physics. So we'll start with the phenomenological one. The starting point for model learning phenomenological features is just starting from the equations of motion of, you know, the physical process that's of interest. In this case, the expansion of the universe, right? We can write down Friedmann equations in this way, and in the standard cosmological model, the cosmological constant is a constant, which means it doesn't really depend on redshift, it doesn't depend on time. Okay, so phenomenologically we break that, and we just say, okay, whatever dark energy is going to have its time dependence. And this is going to modify, you know, Friedmann equation, the behavior of the Hubble rate, and it's going to, you know, influence all sorts of distance determinations. On the other hand, we can play the same exercise at the level of perturbations, where we know, you know, in the standard cosmological model, how structure clusters. Basically, we take the Poisson equation, right, that relates the gravitational potential to the density contrast, and we can take, you know, the fact that in the standard cosmological model, the two general relativistic gravitational potentials are the same, and we simply break these as well, right? So in the case of the Poisson equation, we break that by adding a redshift-dependent gravitational constant. You can imagine this, you know, as basically a modified gravitational constant at cosmological scales, while we break the equivalence of these two gravitational potential by adding another function. And we can think of this function as the gravitational constant for light, right? It's a prediction of general relativity that light gets deflected by intervening gravitational potential. By how much? That's basically the value of G for light. Oops. So one of the things you can notice is that all these three functions that I showed you have the slight inconvenience that they are functions of redshift, so functions of time. And the idea behind model learning is to try to cope with this time dependence. And if you approach so the idea now is that we want to span entire model classes by trying to estimate these functions directly from the data. And obviously, if you approach this problem naively, right, that's clearly impossible. A free function of time is an infinite dimensional space. And if you ask me, it's very inconvenient that our data sets are always going to be finite, right? So there's basically no hope to begin with. So fortunately enough, machine learning techniques like Gaussian processes come to the rescue because there's the realization that while the space of all free functions of time is infinite dimensional, the space of band-limited functions, of slowly varying functions, that's finite dimensional. And if you want to think about this intuitively, this basically goes back to Fourier analysis, right? When we study Fourier analysis, we know that we can decompose an entire function in Fourier modes. If the function that we are dealing with has a finite frequency content, then that's a finite dimensional space, and we can estimate that with finite data. So that's the idea behind the techniques we use to cope with these unknown time dependencies that arise naturally in cosmology. And the idea is that we are going to estimate these functions of time by imposing a correlation between their values at different times. If you think about that, if you want to think about that intuitively, we have, in cosmology, we have this expectation that cosmology goes on the Hubble time, right? That something that's of cosmological origin would evolve on giga-year timescales, right? And estimating these functions of time basically requires us to make this statement quantitative, right? So that's basically the exercise that we have done. We have spanned many, many theories to build our prior expectations on what's the typical time scale that a theory of that modifies gravity would show up, right? And this is what I'm showing here as this theory correlation. And this is truly a prior that we obtained in vacuum. No reference to the data, just we spanned, we went through billions of models, all computer generated, and then just asking the simple question, what's the relevant time scale that's, what's the relevant time scale for the dark energy density and the two gravitational constants. And as you can see, so this is the case where we have mild correlation in the sense that we basically don't enforce anything, and we see that these three functions are uncorrelated between each other, right? These blocks are basically zero, and then there's some correlation within the single functions. But when it comes to concrete models, we can see that these are highly correlated, and we can understand that by a specific physical model will generally modify everything, right? Will tell you a complete story of how the gravitational or how the two gravitational constants would behave with respect to each other. And it turns out that they are generally very correlated. So this basically cuts out the infinite space of functions and allows us to take these three functions of time and then estimate them through with data. And this is what we see here, right? These are the three functions of time I described: dark energy density, gravitational constant for matter, and gravitational constant for light, estimated with basically all the cosmological data sets that we had available, from CMB observations to the clustering of large-scale structures. And I really want to show you this image because that's basically gravitation as we learn it directly from cosmological data. And there's many interesting things in this figure. You can see that when we have very mild correlations, very mild time correlations, we see that the dark energy equation of state oscillates in time. We'll get back to this. We can see that there's significant deviations in both cases in the gravitational constant for light. You see that this basically deviates at about a couple of sigma. And I'll describe in a moment why these type of things happen. As you can imagine, these things are related to the existence of cosmological tensions that somehow these reconstructed models are trying to explain. Understanding these complicated plots with these time reconstructions takes a little bit of statistics, and especially because, formally all these contours are very high dimensional spaces, right? There's at least 20 beams, 20 values for these functions are varied freely, so that's 60 extra parameters. You can imagine that we are then projecting to this plot. So it takes a little bit of statistics, and here you see, for example, the spectrum of signal-to-noise ratio of deviations from the standard cosmological model. And as you can see, for example, the signal-to-noise ratio of deviations from GR in the gravitational constant for light bumps up as we add observations of large-scale structure clustering from the dark energy survey, for example. And I'm also showing you this because there's a couple of fun facts that you can do after the fact, after you're reconstructing the entire thing. You can basically start asking questions to your reconstructions, and one of them that you can ask is, okay, we want to test deviations from the standard cosmological model, so that's the signal-to-noise ratio of this reconstruction with respect to 1 being GR. But you can also ask, okay, what's the signal-to-noise ratio? What's the significance of this guy deviating from 0? So what's the significance at which we are able to measure G for light and matter in cosmology? And it actually turns out that we basically detect the clustering effect of gravity in cosmology at about 20 sigma, and light deflection is detected at about 32 sigma. And this is on a lighter note because once we started doing this, I would have expected a slightly higher result, right? So the fact that gravitation exists in our universe, I think, is something higher than 20 sigma, at least morally. So the reason why these the reconstructed pattern deviate from the standard cosmological model goes back to cosmological tensions that you basically see here depicted. And in fact, we can see that basically this is the space that concerns, this is the same plot as before, the amplitude of galaxy clustering, the Hubble constant, and you can see that basically one of these two tensions, the one on the clustering of structure, is significantly relieved, while the tension over the Hubble constant is only partially relieved. And this is the reason why we were seeing deviations in the gravitational constant for light, right? That's responsible for light deflection. That's responsible for the effect of weak gravitational lensing, and that's basically the tension that this guy is relieving. On the other hand, the redshift dependence of dark energy density, that's telling us how distances behave. So that's the thing that's trying to accommodate the different values for the Hubble constant. And one of the very interesting results of this work is that, which is also a sweet and sour result, is that, the Hubble constant tension is only halfway relieved, right? Somehow we can't go on target, which was my initial hope, right? We are literally throwing at the data infinite freedom, yet we can't really solve one of these two tensions. And the reason goes to the heart of how the Hubble constant tension is really phrased. That's a 0-point calibration of supernovae and BAOs from the CNB, right? So a working model that would solve the Hubble constant tension needs to enter here at high redshift and exit here at low redshifts. And due to the fact that we can't really oscillate too much because we have a correlation prior, there's basically no way of doing that smoothly and going on target. So that's the physical reason why this type of reconstruction can't really relieve the Hubble constant tension. Now, we can do other interesting things and make other interesting statements once we have these results. And one of the things that we can do is basically check for consistency relations, theoretical consistency relations, right? I told you before that when we have classes of models, specific classes of models, they usually tend to modify gravitational constants in a very specific way, and usually they enhance both, right? So this is the heart of this consistency relation that holds for relatively simple models of gravitation, which is, if the gravitational constant for light is enhanced, so should the gravitational constant for matter. And we can just test that a posteriori, and it turns out that it's pretty consistent in both reconstructions. Then what both reconstructions show is that basically we can live with a model that's as simple as a single scalar field model. Another interesting result that we can obtain a posteriori is whether simpler things would work, right? This is usually what's done when we have no idea of the redshift dependencies of these two guys. We usually parameterize them, and I'm sure this is done throughout different fields, right? You have a function of time, you just use a simple parameterization instead in terms of power laws or something like that. Having these very general results, we can go back and test it, see if that would have allowed us to recover the reconstructed behavior that we are seeing. And it turns out that basically that's impossible. And I think that assuming simpler parameterizations for these two gravitational constants would give you biased results. And I think this is especially relevant because this is a no-go results. The situation in the future is not going to be better, right? Experimental complexity always increases. And this is telling us that already the complexity we have in the experiments we are doing can't really be captured by simple parameterization. So that's why I think these types of exercises are going to be increasingly relevant in the future. So this is it. That's it for phenomenological reconstructions. Now I want to show you an example of physical reconstructions, where we specify a class of physical models and we try to estimate their properties from data. And the idea here is that we would restrict to scalar field models for dark energy and gravity. And the only assumptions that we are willing to make, we want to cover the entire class of these models. So we want to just assume the symmetries of our universe, homogeneity and isotropy, right? And then we want to restrict ourselves to large cosmological scales. And it turns out that, it was done in the past. It's possible to describe all models of gravity and dark energy that basically obey these two statements and that have one extra scalar field, that have no Lorentz violations and satisfy the weak equivalence principle. And the idea is that, what has been done in the past is basically just writing down the most general theory that satisfies these symmetries. And that's truly just, a geometry exercise, right? Where we take, the homogeneous and isotropic universe, and we write everything that's compatible with that symmetry, which is not 4-diff invariance, but it's only 3-diff invariance. And all it takes is a little bit of geometry. But after this complicated exercise, we can condense the freedom we have in defining this type of models into a set of 5 functions of time. And again, it shouldn't be a surprise that these are functions of time, because everything in cosmology can depend basically only on time. And potentially not surprisingly, the first function is a cosmological constant that, in the standard cosmological model, it's constant. In general, has a time dependence. And the same goes for the gravitational constant. The gravitational constant is a number. And if we allow for the freedom we have in scalar field models, then this would become a function of time. And then we go on with more complicated properties of scalar field models, kinetic energy, different types of couplings, setting the speed of sound of the scalar field, up to the point where we consider a modified speed of gravitational waves. And and some of these properties we might usually connect them to models of dark energy, like time-dependent cosmological constant. Some of these properties, we would usually associate them to modifications to gravity, like a modified gravitational constant, right? So these type of approaches allow you to blur the line between these two. So I'm going to interchangeably talk about dark energy and modified gravity models because they are basically just the same thing. And again, you see we have 5 functions of time, same exercise as before. We developed the theory prior by scanning through billions of models. It turns out a third of an E-fold is a good time scale if you're interested in this type of details. But basically, once we assume that we have a time correlation between these functions, we can estimate from the data. And this is basically the result we've got. And as you can see here, there's many things to unpack because this is a significantly more complicated plot with respect to the previous one. But one of the things I want to stress is basically that this is gravitation in our universe as we obtain it by only using symmetries and data power, okay, which I find really remarkable. And one of the results is that, for example, the cosmological constant can only run, it's constrained at all redshifts of interest at the 100% level, which is usually much less than much weaker than what we might have expected. You might, a zero cosmological constant is not entirely excluded, and it might be of interest to somebody that there's a little bit of space for the cosmological constant to flip sign, especially if you're interested in string theory. On the other hand, the Planck mass is constrained to vary at about the 30% level at all redshifts, and one of the interesting things is that this deviation here is statistically significant. So it goes, the gravitational constant goes to 0 today, but seems to have a different values at earlier times. And this difference is statistically significant, and we'll come back to its interpretation later. On the other hand, this function here that sets the speed of sound of dark energy perturbations doesn't really have a limit to the standard cosmological model, so this is not really statistically significant. These functions just doesn't exist in the limit of the standard cosmological model. So we can't really use it to gauge deviations from it. On the other hand, the speed of gravitational waves is constrained to vary across redshift at about the 40% level at all times, and which is I think a remarkable result, considering that this is coming from cosmology alone. The speed of gravitational waves, it's not a necessary part to the story that I'm about to tell you. There's obviously all the cases where this is fixed to luminal as a result of direct observations from neutron star mergers. But I like this picture where I'm keeping it free to see what cosmology has to say about it. And one of the most interesting feature, I think, is that these type of reconstructions relieve cosmological tensions to basically about the same performances as we saw before, right? So the tension over the amplitude of galaxy clustering is basically totally relieved. The tension over the expansion rate of the universe today is relieved halfway. This yellow guy is when we fix the speed of gravitational waves to 1. You see, it doesn't really change much. But basically, the reconstruction, this type of physical reconstruction achieves the same performances as phenomenological reconstructions. The interesting part of it is the fact that the way in which that's achieved, we saw that through phenomenological reconstructions, we had 2 ingredients. One was modifying distances, the dark energy density as a function of time. One was modifying light deflection. So 2 ingredients for 2 tensions. In this type of physical reconstruction, the only thing that's really relevant is this running of the Planck mass, which is the way in which the fitting machinery realizes that it can basically kill 2 pigeons with a stone, right? So the running of the gravitational constant would change both distances and the clustering of light, and the fit finds that as a way of doing both tensions at the same time to basically optimal performances, yet not totally on target. The fact that we have now a physical reconstruction allows us to make different types of statements with respect to the previous one, because now we have basically access to specific models. And I want to show you one example of the type of results that this technology unlocks, basically. And this is basically going back to one of the simplest models of dark energy that has been proposed, quintessence, one scalar field, one free field, no weird couplings or any other things. This is in one-to-one correspondence with the running of the cosmological constant. And then, we can estimate this from data. We can get constraints on the quintessence potential. So the idea is that physical reconstructions would allow us to go all the way from data to specific theory models, rather than stopping at a phenomenological level. All it takes to do that is Min-Soo Park, that's a grad student working with me in Penn, that basically led these type of exercises. So we start from the running of the cosmological constant. Here you see it's a little bit different from before, because there's only these functions that's being estimated from data, and then we can reconstruct the scalar field potential. Right, and it looks like this. It's tilted down because, as we know in cosmology, a field to roll has to overcome Hubble drag, so it needs to be tilted down a little bit. And in this other plot here, you can see what's called the dark energy phase space. Now, this rather obscure construction was something that people used, 30 years ago when cosmic acceleration was discovered, to try to gauge whether there were natural solutions to the problem of cosmic accelerations that you can see here. These yellow lines are from historic models that tried to solve the coincidence problem of dark energy by basically having attractor solutions, right? And then, having all this weirdly behavior in phase space. And now, since we have the entire reconstruction of the whole family of models, we can ask, okay, what's the allowed range? So the allowed range goes between these two bands, because this is the future, which we very inconveniently can't really see. This is too far back in the past, and basically our data live here, and where our data can express its constraining power, it basically is killing this entire phase space. And I really like this picture because it shows, the kind of progress that has been done on dark energy phenomenology in these last 20 years, right? 20 years ago, people, thought we could be living in a universe that does all this interesting stuff. As far as these models are concerned, the data don't really like that too much and basically squeeze us in a corner of that space. But that's not the end of the story, right? Physical reconstructions allow us to ask questions to our data of increasingly high theoretical value. And I want to show you basically the end point, which I think is theoretical statements at the highest possible level concerning string theory, right? So, which I am by far no expert on, but what I've been told from my string theory colleagues is that not every low energy quantum field theory that's coherent can arise as a low energy limit of string theory. And string theorists have been very interested in mapping the boundaries between, what can come from string theory and what cannot come from string theory, right? And in a program that has been called the Swampland program, and what they have found is basically that, they have put limits in cases in which you have an extra scalar field that's coming from string theory, and then that scalar field has to have some properties. And in particular, the motion of the scalar field has to be limited in Planck units, and the steepness of the potential can't really be too small, right? Honestly, I have no way of gauging how good these statements are, but that's not really something that bothers me. We have the entire reconstructions of these entire families of models. So we can just look down, go out and look for these, and this is what we have found, for example, right? So, in our universe, if we have a single scalar field, then, the field space that the scalar field is traversing is, limited, to be significantly less than a Planck mass, which satisfies the first type of conjecture, while the steepness of the scalar field potential is comfortably within bounds. So I've removed here the absolute value to show you in this plot. This is negative. As we saw, the potential needs to be tilted down a little bit to win Hubble drag. And this is, I think, the most interesting to me, right? Because this statement here, it's rather vague, right? You have a statement that tells you, okay, this thing is order 1, and my understanding is that this was, inspired by concrete constructions in which this value for the steepness of the scalar field potential were like something like 1.7, 1.2, and so on and so forth. And what this plot is telling us is that, this is the time to make these constructions more concrete, because this is the time where, cosmological data start being sensitive to this type of questions. A value of 2 is completely ruled out by data, while basically we have a 0.5 width that we can probe with cosmology. So we are basically at the level where cosmology can inform some of these decisions. And this is basically it. I've shown you today that we have enough data power to make to constrain dark energy and gravity properties in a way that's model independent with minimal modeling assumptions, right? And this allowed us to discuss a wide range of topics, ranging from phenomenological constructions to model independent statements on string swampland conjectures. I hope this was the first time where you have seen data directly speaking string theory language, right? And at present, basically, this gives us some observational go, no-go theorems for late-time solutions of cosmological tensions. That can't really happen. We can solve some tensions at late times concerning the growth of cosmic structures. We can't really solve tensions related to the Hubble constant tension. And I think in this respect, the future is bright. Current constraints are, once we free up this space, this general space, current constraints are at the level of 10%, and we are actively working to try to bring these constraints to the 1% level, to basically see if we shrink these error bars, if something pops up. And current data sets can constrain, basically after you do the statistics, 15 properties of dark energy. That's the number of modes in these reconstructions that turns out to be constrained by data, which is significantly higher than what's expressed by simpler parameterizations. Then it's significantly higher than the number of cosmological parameters we have in our standard cosmological model. And it basically tells us that there's 15 properties of dark energy and gravity that we know. And I think this is basically changing our perspective as we gradually move from testing models of dark energy one by one, trying to peek through the dark side of our universe, to trying to learn the properties of the dark side of our universe directly from cosmological data. Thank you. Okay, guys, do you have any questions?
If you have questions, we need you to use the microphone so that people outside can hear. Okay.
Thank you very much for the nice talk. I have a very naive curiosity. So you showed us sort of data-driven methods to learn information, and then a class of specific models. So if I think, for instance, about particle physics, there's usually like a middle point which is constructing effective field theories. Is anything which is a bit more like systematic than trying random things? Is there something that one can do in this context? Or?
Yes, so I forgot to mention that this type of construction is called the effective field theory of dark energy. So that's basically in the spirit of that approach. The difference, I think, is that here we end up with free functions of time, which makes our life significantly harder because of these functions of time thing. But yeah, one of the I think very interesting areas of intersection between this type of constructions and more formal construction. This is still fairly phenomenological. Is that this type of thing would give you a handle on the physical viability of models. So you can actually take this construction and ask, okay, if I start with this type of functions, is my theory well built? Do I have a positive kinetic energy, or this type of statements? And I think one promising interface is understanding whether there's additional requirements that we can impose on these theories from effective field theory techniques to shrink basically the space, right? 5 functions of time is still a very large space. Anything that kills a little bit of that helps, whether it's theoretical or whether it's data. So that I think it's an interesting area of intersection.
Okay, thank you.
Other questions? Maybe from the students you can speak Italian if you want. Okay, otherwise let's thank Marco again. Grazie, Marco.
Thank you, guys.